Okay, this is the last video for this lecture, and I want to start with image spectrometry or imaging spectrometry. Same thing. So it is the simultaneous acquisition of images in many relatively narrow, contiguous, and or non-contiguous spectral bands, which means that when a sensor is using image spectrometry technology, it means that this sensor has dozens or even hundreds of bands, and each band is very narrow, which means each band has a very narrow bandwidth in terms of spectral. Throughout the ultraviolet, visible, and infrared portions of the spectrum. So usually we use another term for image spectrometry. It's called hyperspectral remote sensing. We call it hyperspectral because it is twofold. Firstly, so many bands. And secondly, each band is pretty narrow. And there are three approaches for image spectrometry. You can use linear array of detectors, or a whisk broom scanner, or two-dimensional area arrays. These technologies, these methods, they're very similar to traditional remote sensing, non-hyperspectral remote sensing. Okay. And the two famous hyperspectral remote sensors I want to introduce here are AVIRIS and MODIS. So AVIRIS is an aerial sensor, okay, aerial remote sensor, airborne visible infrared imaging spectrometer. So in short, it's called AVIRIS. So you can see here from 400 nanometers to 2,500 nanometers, there are 224 bands, and each one with a 10 nanometer bandwidth, which means when this sensor is capturing information from the ground, okay, there are actually 224 images will be produced after each shot. Okay, after each taking of the image of the area, there are 224 images. Okay, so if you stack them, you have this so-called spectral cube. We call it cube because you can even consider that these images, they are continuous to each other. They're continuous in terms of the spectrum. So as a result, you can create a very, how can I say, not smooth, but a continuous reflectance curve for a specific object on the ground. Okay, just like this. But if you compare this technology with traditional remote sensing, for example, Landsat or Spot, they usually have less than 10 bands. For them, it's not possible to produce a smooth curve like this. If you only have 10 readings within this spectrum area from 500 to 2,500, if you only have 10 readings, or in other words, 10 bands between these two wavelengths, how can you create this continuous a smooth curve? Not possible. So that's the advantage of hyperspectral remote sensing. We can accurately capture the details of what? Of a spectra of objects on the ground. Okay. So another one is called MODIS, moderate resolution imaging spectrometer. It is a satellite sensor, so it's not airborne. Okay. It's in the outer space. So the spectral range for MODIS is from 0.4 micrometer to 14.4 micrometers. So this is the thermal band, right? It's in the thermal infrared range. And 0.4 is a little bit shorter than blue light, which means it's violet. Okay, so the spatial coverage here, spatial resolution. There are how many bands? 29 plus 2, 31 plus 5, 36, 36 bands, right? So 2 bands have a spatial resolution of 250 meter, 5 bands 500 meters. The other 29 bands, they have a spatial resolution of 1,000 meters or 1 kilometer. And image the Earth once every 1 to 2 days. Okay, so every 1 to 2 days, this sensor can just cover the whole Earth. Okay, and MODIS is a whisk broom scanning image radiometer and 36 bands, right? So 20 bands, they are from visible infrared to mid-infrared, and 16 thermal bands. And you should also be noted that MODIS sensors, they are mounted on Terra and Aqua 2 satellites. Okay, there are 2 satellites mounting MODIS sensor. Both satellites operate in sun-synchronous orbits at 705 kilometers above the Earth. That's the reason why you have a very short revisit time or revisit period for MODIS, because there are 2 satellites, right? They're working together to observe the whole Earth, and they both have MODIS on them. Okay. And next, for the last part of this lecture, I want to give a little touch on active remote sensing. I mentioned this before. This class is called remote sensing applications, right? But it's to be more accurate, it should be optical remote sensing or a passive remote sensing applications. Okay, because another category of remote sensing is called active remote sensing or microwave remote sensing. They do not use active remote sensing systems. They do not use sun as the energy source, and they use sensors themselves as energy source. Okay, so they are for detecting distance from objects instead of reflectance from objects. Okay, optical remote sensing systems, they are trying to retrieve ground information through the reflected energy from objects on the ground. Reflected energy, what is that? Usually it's reflectance. It could be other parameters, but reflectance is the main character here. But for active remote sensing systems, they detect distance from objects according to backscattered energy from the terrain. So backscattered energy is can also be considered as reflected energy, but this energy is not from sun, it's from sensors. Okay, so the most widely used systems include 2 categories. First one is called radar, radio detection and ranging. So based on the long wavelength microwaves from 3 to 25 centimeters. Okay, it's not nanometer, it's not micrometer, it's centimeter, which means that the wavelength used by radar system is pretty long. And another category is called LIDAR. This is more advanced. Okay, it's called light detection and ranging, based on the relatively short wavelength laser light. It's not microwave, it's laser light, which means that this energy, this light energy, can travel along a very accurate distance for very long time. So for example, 1.0 micrometer. So the wavelength used by LIDAR is not as long as the wavelength used by radar, but LIDAR is also for what? For ranging, for detecting distance. And the third category, it's a kind of remote sensing, but it's not widely used. Okay, it's called sonar. Sound navigation ranging is always used in oceanic application, for example, on a submarine. So usually we don't consider this as a very typical remote sensing method, but I think I should list it here. But mainly you should know when we're talking about active remote sensing system, it's mainly radar, systems or LIDAR systems. Okay, but sonar, let's just understand what that is. That is good enough. It's based on the sound waves through a water column. Okay, so it's good for the detection of riverbed, ocean bed, or objects under the water. So this is a very typical radar remote sensing process. Okay, pulse of EMR is sent out by transmitter through antenna, is of a specific wavelength and duration. Okay, for example, it has a pulse length measured in microseconds. Okay, the wavelength is pretty long, and the pulse will just sustain for a specific time. Okay, and you can say that this distance between the target and the satellite is the distance you want to measure. Okay, the pulse is transmitted from satellite, from sensor to the object, and backscattered by the object and received by satellite again. Of course, you need other parameters, for example, time. Okay, accurately measuring time is very important for radar and LIDAR. Okay, and you use time, and you use the speed of light, you use the different angle and elevation of the satellite. All these parameters together, you can calculate the distance between the satellite and the target. Okay, and the wavelength used by a radar system is obviously longer than visible near infrared or infrared energy. And the advantage of using long wavelength microwave is that this part of the spectrum, this part of EMR is pretty good at penetrating clouds. Optical remote sensing is not capable of penetrating clouds, which means that even the sensor is right above you, the aircraft is right above you, or the satellite is just flying over your area. If it is cloudy, if the sky is cloudy, there is no way they can do anything. Okay, they cannot take any picture off the ground because visible light, near infrared light, they will be blocked. They will be blocked by clouds. But microwave does not fear cloud. Okay, so microwave energy usually measured in centimeter because the wavelength is just too long. It's not convenient to use a very small unit, for example, a micrometer or even a nanometer to measure it. Okay, this one is more advanced. I mentioned that, right? LIDAR, light detection and ranging. So mirror sweeps laser beam, okay, across the ground. Okay, here is the laser scanner. It will sweep the ground. It will sweep the ground just like the whisk broom sensor, the whisk broom optical sensor, right? And the plane is flying over the area, and measure distance to target by measuring time interval between transmission and return of reflected laser pulse, which means that when the pulse is short, a time is recorded. And when it travels to the ground and reflected by the object and arrives at the sensor again, another time will be recorded. So this time interval between the first time record and second time record is the time used by this laser pulse to travel to the ground and get back to the sensor. And we know that the speed of light is considered a constant. So you know the time and you know the speed. So it's pretty easy to calculate the distance. So it's just that simple. But the technology is very advanced because it's pretty hard and expensive to build a laser scanner and also other components of the sensor. Okay, we need to use GPS to record aircraft position, ground reference, and use ground reference stations to do that, to record the position of the aircraft and the more accurate position for the sensor. And also we need another component called IMU. is called an inertial measurement unit, measures the angular orientation of the scanner relative to the ground, which means that the position and the gesture of the sensor should be accurately recorded, and also the time needs to be accurately recorded. You need a high accuracy clock. Okay, a LiDAR was not that accurate because maybe 4 decades ago or even 3 decades ago, we didn't have GPS and IMU. So the position and gesture cannot be accurately recorded or monitored. So accurate distance measuring was not possible, but it's possible today. And today, LiDAR is not only for scientific applications. Okay, on a lot of high-end cars today, there are LiDAR sensors around your car to detect the distance between the car and the surrounding environment. And this distance measurement is crucial to auto driving or other security systems of your car. Of course, it's not commonly used because it's very expensive. So you can only find LiDAR sensors on high-end luxury cars. I mean, today, even a very normal car, we have maybe a radar system or a camera to help you avoid pedestrians or other cars so you do not run into them by accident. But they're not accurate. They're not as accurate as LiDAR. So LiDAR sensors are only used on high-end cars. So next time when you're trying to buy a good car, or you're browsing pretty good cars online, you can notice, okay, you can try to find if this car has LiDAR sensors around. If it does, it must be a very expensive car, okay, at least for today. Maybe 10 years later, LiDAR is not that expensive anymore, but for today, it's a luxury, how can I say, a luxury component of a car, okay? And the image produced by LiDAR sensor can be considered as something called point cloud, formed by discrete points, each recording the altitude of a location. Because LiDAR sensor does not care about the reflectance in visible light range or near infrared, each point is not a reflectance of EMR. Each point's data or each pixel's data is actually the distance between that location and the sensor. So as a result, we have something called point cloud like this. Right? We have points with different colors here. Some of them, they're blue, some of them cyan, green, yellow, orange, or even red. Different colors or different hues here, they are used to address different distance or altitude or elevation. So obviously we have two very flat platforms on the left side and the right side of this point cloud. They are what? They are just normal land, flat land, okay? And here we have a river. And the blue area here, blue points, they're saying that, okay, these locations, they have pretty low altitude or elevation because they are at the bottom of the river. They are river bed. And then between the bed and the two banks, we have other locations between them, right? They are addressed by cyan and green, which means compared to all those locations at the bottom of the river or on the bank of the river, they have relatively not too high, neither too low elevation, okay? So you can see here, it is actually a 3D environment of the area of interest. We can differentiate different objects with different heights or elevations. So it's very convenient, right? We can use it to create 3D environment. For example, like this, a very huge stadium here. And so we have surrounding vegetation, right? There are small grains. We can see that each grain is a canopy. And we have an urbanized area on the left side of the stadium because we can see small squares. Each one is a building or small polygons, not necessarily squares, right? And if we overlap this LiDAR image and with, not like that, we overlap a true color image on this LiDAR image. This is the result. So here we can see some of the objects, they are high, some of them, they are flat, and they have true colors. So this is a very accurate, what? 3D map on a 2D plane. Okay, so on the left side, we have the LiDAR image. On the right side is a combination, or you can say it's a stack of a true color image and the LiDAR image. And that true color image is just like the skin of this LiDAR image. So together, it's a vivid, very real, real world image, right? With true color, and we can differentiate, in general, differentiate the height, different heights of different objects. And of course, we can rotate it, okay? Because we have a 3D image here, we can use ArcGIS and other software. Some software, they are specifically, they were developed for LiDAR data to create this 3D environment, to look at the stadium from another angle instead of right above, right? So LiDAR is widely used in 3D environment creation, of course, real world. And distance detection is actually important when we care about forests, urban development, or even the security of a car. Okay, this is the end of this lecture, and I will see you in the next video and lecture. Okay, thank you.